Okay, so now we're really going to take a look at the technical EMR architecture, what this is going to look like, and some of the things that we should watch for. So in general speaking, as you can see from this page, there are actually three different kind of groups. I don't know whether you pay attention to this or not earlier, but there's master groups, there's a core group, and there's a task group. And those groups are taking care of different kind of responsibilities in terms of the software is being installed, in terms of from a kind of availabilities perspective, what's the requirements for different kind of group. There has different kind of requirements and definitions. So so basically, master node is a managed resource of cluster, schedule jobs on worker instance. Now think about master node is as the brain of the kind of a whole cluster. From Yarn's perspective, from HDFS perspective, so master nodes is able to combining those kind of services into a kind of a single work group, and this work group able to kind of start broadcasting and managing the clusters from the master node perspective. So as you can see, we from the whole cluster architecture perspective, the one single point of failure is going to be the master node. So master nodes will, if master node goes down, your whole cluster will basically won't be functional as expected, because it has no kind of leader anymore. So at that time, you have to think about if this is a long running cluster, you have to think about what is going to be the architecture, what is going to be total number of instances for a master node in order for your cluster to be sustainable. So core nodes is basically, think about this, the main difference between the core and the task nodes is whether HDFS is being installed or not. So HDFS is not a mandatory kind of services for your cluster. Depends on your workload, but HDFS, generally speaking, is not a mandatory kind of services for majority of the process. So people using so the cluster using HDFS to for caching some of the logins, some of the user informations, only. So really, it's for management purpose, at this point. But one thing that we see in common between the core nodes and task nodes is the like they basically both chip in CPUs and memories to combining your computation cluster. Okay, so Amazon EMR environments have 2.3. So as you can see, there's master instance groups, and so contains one master nodes, and master contains the cluster. It runs the name node, which is the HDFS, and then monitoring the health within your cluster, and also having a resource manager, which is for Yarn. So core instance groups contains all core nodes along with HDFS storage. At least one core instance must be running, which is, as we said earlier, is not mentoring for majority of your applications. However, from the cluster perspective, it still requires HDFS to caching some of the information like users, like some logins and stuff like that. So including data nodes and node managers daemons from this cluster, because you have to run HDFS in here. Module review. As time permits, your instructor will facilitate this kind of following. Okay. Let's first talk about what are the primary Apache Hadoop components. So I think we talk about what the components available within this entry page, but so for some of the mandatory services within Hadoop components for EMR. So we talk about there's Yarn, which is the resource manager for the whole cluster. There's a HDFS, and there are a bunch of Hadoop common libraries, right? Which is kind of available on the class path within the cluster. Second is list 2 applications for which Apache Hadoop is not suitable. So Apache Hadoop is not suitable for small data and for kind of real-time ingestions and data processing. It's not suitable for that. Let's go to the next page. Yeah. So using Hadoop for data processing in terms of the advantage is handling uncertainty, handle different data varieties, providing flexibility is handling data volumes and velocity. 2 issues, capacity planning, capacity scaling, running experimental and ad hoc workload, administration, storage complexity, and monitoring. So those are some of the issues running on premises Apache Hadoop, like Hortonworks and Cloudera, and comparing with the benefits of using EMR in AWS. Launching your cluster. So there's 3 ways to launch a EMR cluster. There's including management consoles, including AWS CLI, including AWS API. So basically, it's really depending on how is the preference from an infrastructure as a code perspective. Different companies have different kind of policies and different requirements for them to to define their best practice for launching their infrastructures. So management console is the one I was showing you guys earlier. So you're able to open up a management consoles and able to click around and then say launch at the last page, right? So you're able to launch your cluster and claim your resource like that. There's another way you can do, which is using an AWS CLI. So AWS CLI is basically, if you remember, so what we are able to do is we're able to say AWS. Okay, so basically it's not being installed. So what we can do is install the CLI from the command line called apt install AWS CLI, and we are.
May I ask, as your experience, like when you're working as data engineer,
Mm-hmm.
how much of the work worked with CLIs, how much worked with let's say API or SDK, how much finished by the console?
That's a good point. Okay, let's go back to this page. So when you're using this page is pretty much for experiments, which means think about if you are having a job that you're going, you need to do, and then at the first beginning, you don't know exactly how much computation resource you need to claim. So what you need to do is you need to go to the consoles and start, trying different kind of options, right? Including, different kind of services, including different kind of initial kind of instance you're going to claim for the cluster, and also including the initial configurations you need to do. So this going to this phase, I'm calling it more like a, from a engineering perspective. This is more experiments. So you need to fully understanding what is the particular process data workflow you are dealing with at this point. So once you have a clear understanding of what you're dealing with, this management console is pretty much, it's a kind of, it's there. It's all for you to experiment. Once you finish, you have a better understanding of what resource you need. You can jump to the next stage, which is AWS CLI. And the way you need to do is, so now I have AWS already installed. So you can do AWS EMR. You can do help. So you can say, you can create a cluster, you can cancel steps and whatever, right? But one thing I want to show you is kind of like a very neat feature for EMR that I think I developed along the way. You can say, click on, let's say my cluster, and click on AWS CLI exports. So for the same configuration that works for your current workload, you can come here, copy, and paste in here, and I hit enter. You're going to having an identical kind of clusters that you were, doing the experiments, right? Which is kind of a nice feature for you to kind of like clone the identical cluster that you were using earlier. So this is kind of like, from a repetitive, and from a infrastructure as code perspective, AWS CLI is kind of giving you the identical kind of clusters, configurations, and also the settings, as what was working last time. So this is AWS CLI. So API is more like if people using Terraform or CloudFormations, what you're able to do is you're able to defining a bunch of parameters, bunch of infrastructure as a code, kind of configurations within that particular, let's call it like workspace, and then you're able to keep track of the versions of what your cluster looks like in terms of all the configurations, and giving you a very stable and reliable way to spin up your infrastructure. So from a work perspective, the most often interactions as a data engineer you're going to deal with is the first two. So, console is nice to do experiments. AWS CLI is more like, once you settle with certain configurations, you want to reduce the human beings' errors, mistakes by, directly copying the working kind of AWS CLI from this console, and then, just spin up the resource like that, right? AWS API is more like, from a project perspective, you have to follow the infrastructure as a code practice. And then you are going to using like Terraform or CloudFormations to defining your AWS resource. So that's kind of, from a day-to-day perspective, you're going to be dealing with those two the most. And this is purely or primarily for the kind of DevOps teams to deal with.
Thank you.
No problem. Okay, so this is a very important topics, transit cluster versus a long-running cluster. So there is quite a bit of debate from the industry as well as from different teams, like which one is actually working better. So the answer is it really depends on the requirements and in terms of the sensitivities from a cost perspective in your company. Like if you are super cautious with the cost, then transient cluster is probably the way to go. But if you are super kind of sensitive with the timing, then the long-running cluster is probably the better way to deal with it. So when we talk about the times difference, it's really talk about 5 to 8 minutes difference. This is how long it really take to starting a EMR clusters from scratch. So as you can see, transient cluster is basically a way to saying, whenever there is a trigger, the EMR computation resource will be claimed, and it's going to be terminated automatically on completions of tasks immediate as steps. So what does this mean? Think about you have a event sourcing process. Like say, whenever you have a job ready in your kind of landing page or landing stage, you're going to trigger you're going to allocating some resource in order to processing this incoming data. So at this point, you have to allocating this resource on the fly by making a bunch of API calls. And once this kind of a cluster is ready, you're able to, in terms of all the services you claimed, you asked, is claiming as healthy. And at this point, you're able to really submitting your job to the young cluster to really doing your job, right? So that's kind of what you're expecting the cluster to do. But let's say, once your computation process is complete, at that point, all the existing resource is going to basically automatically shut down. And then, the whole cluster will claim as a exit, and then really to, terminating any existing resource from this cluster's perspective. So at that time, you're really saving the cost and, reducing your kind of, footprints in terms of how many resources you're occupying within your account. So that's kind of the benefits of using a transient cluster. Typically read code and data from Amazon S3, and do not persisting HDFS data after termination. So the last point is super kind of important, and also if you think about it, is actually making sense that as we talked about this earlier, the transit cluster is a way for you to basically quickly spin up the resource and shut it down. But since HDFS is only available during the periods when the transit EMR cluster is up and running, but once the job is completed, the EMR cluster is going to shut down, which means your HDFS is going to automatically shut down. So if HDFS is terminated, that means all the data you persisted over there during the middle of the computation will get lost. So at this point, you have to super careful and understand that you do not persist any important informations on HDFS within a transit cluster, because by the end of the life cycles, the data will be gone when all the computation is completed. So after we talk about transit cluster, let's take a look at the long-running cluster. So long-running cluster are not terminated automatically, which means once you start a cluster, the only way to get this cluster terminated is either your kind of invoke the termination signals to the cluster, or the AWS is running into some kind of service failure mode, which means terminating all the kind of clusters. So it's our job to be interactively submitted via a master nodes, Step API, or other scheduling tools. So as you can see, the way to submitting the jobs into EMR cluster has several kind of flavors. So let's talk about them one by one, and because this is actually quite important and quite interesting to understand how this is working under the hood. So from EMR perspective, let's open up the EMR cluster. So EMR, you have a master, you have a worker, and then from a user perspective, you have several ways to submit a job. So first of all, what you can do is, let's talk about 3 ways one by one. Option 1 is to SSH to EMR master node and call Spark submit. This is one way of doing it. So, and this is actually one of the kind of convenient way of doing some of the kind of experiments by just directly SSH into EMR master node and doing the submission over there, right? This is one way of doing it. The other way of doing it is by creating a edge node and have the edge node to submit the job to the EMR cluster. So what this means is you basically, from a user perspective, you're creating another node, and this node knows how to talk to EMR master node and the worker node. And then you're able to submit a job from the kind of edge node. So this is another way of doing it. So option 3 is basically register a step with EMR cluster. The step have to include the mandatory information like Spark submit, the mode, the executor config, and so on and so forth. So by default, the capacity is 1. Is 1, and you can change this accordingly. So changing the total capacity to a higher number is some feature available, I think, recently, which means before the only option is to doing the submit through the SSH. But recently, since this register steps for like a higher concurrency is available, people prefer to do this register step over the SSH because this requires more kind of works, from a scripting perspective. But this one is a little bit straightforward and easier to maintain. And for our final project, we're going to do through this fashion, which is register a job. Persist HDFS data after the tasks are completed. So this is optional. Like if you need to persisting data on HDFS, you're able to do it. Otherwise, you basically, for 99% of the case, putting data on S3 is always the best, way to, securing your data. Transit clusters are better for intensive and interactive ETL processing jobs, save on cost. So I can give you an example of, the kind of a typical use case that I'm actually using in my current job. So I'm using transit cluster to deal with a massive kind of parallel processing works that involves around 12 different data sources, and the total records that actually returns are around 38 billion records usually per day. And as you can see, 38 billion records in total. From the storage perspective, we talk about a couple hundred kind of gigabytes per run. So from a cost perspective, from a resource perspective, I have around 4 kind of terabytes of memories, and I have around 500 CPUs in order to complete a job and make the job come back within a reasonable kind of fashions. The reason is because our job is daily run, and there is downstream teams actually relying on these computation results to do their next stage of kind of decision making process. So I have to making this process running as fast as possible, and also within a reasonable amount in terms of the cost, right? So my kind of type is R5 12 extra large. Let me show you really quick in terms of how much computation power is able to bring you. So R5 12 extra large, it has 48 CPUs, 384 gigabytes of memories, and it has 10 gigabits per second in terms of network throughputs. And the EBS stands for elastic blob storage. We talk about megabits per second is around 9,500. So I have around 12 instances like this, so which is around like a 500-ish kind of a total CPUs to do my computation, and over 5 terabytes of memories. So because my job is more CPU intensive, and so after I did the calculations, like this instance type is making the the most performance in terms of per dollar ratio for the kind of computations. And we can take a look at in terms of what's the cost for this instance type. So we talk about $3 per hour for a R5 instance. This is on-demand price. If you do a reserved instance, it's going to be much cheaper. But you can see if I have 12 instances, so we talk about the job is finished within like 40 minutes-ish. So we talk about a 65% of the $36, right? Let's see how much each of the day is going to cost me. 3 times 12 times 40 divided by 60. So it's cost me $24 to finish the computation, every day, right? So per month we talk about 700 something. If a similar process that you have to deploy, let's talk about 30 days. So we talk about 12. We talk about under 10 grand. You're able to finish your heavy computation process within this amount, right? Versus if you trying to having on premises a kind of data center, like you have to pay a couple millions at least in front in order to ordering all the kind of resource and then installing and putting the wires together, right? So think about how much money you have to pay for that. Long-running clusters are best for jobs that run on a regular basis, less than an hour between jobs, or even an extended period of time. So let's say, for example, in my long. By the way, in our architecture, we have both transit cluster as well as long-running cluster. So long-running cluster is typically dealing with small incremental files that come in regularly, and it doesn't really make sense for us to spin up a cluster and shut it down if we have, let's say, like 300 jobs every day. And then, you think about if you spin up and down 300 times, and how much additional cost you have to pay for this in terms of, now, by the way, when you spin up the resource, you have to pay for it, right? So let's say if you, spin up 300 times 7 minutes divided by 60 and times, let's say, I don't know, let's say $2 per instance. So every day you have to spending $70 just for spinning up the EMR cluster, right? Versus how much money is going to save you if you purely operating as a long-running cluster, right? So you do the cost comparison, you will understand which kind of fashion is working for you the best from a cost as well as performance and latency perspective. So let's take a 20 minutes break. Let's go get some food and come back around 7:50 and continue. We're going to finish this kind of EMR tutorial. And after that, let's do some exercise as well as we can talk about, hoodies or Delta Lakes after, if we have some, time to kill today. So long-running cluster are best for jobs. So we talk about this long-running cluster. So machine images. So as you know, EMR cluster is nothing but a bunch of EC2 instance that install a bunch of customized software and then combining them together and then returning you a functional kind of computation cluster as a whole. So from an EC2 instance perspective, what you're able to do is you're able to providing a custom AMI images for your launch EMR cluster. So this is kind of like an optional that you're able to define those kind of configurations from there. So if we are taking a look at our cluster and then just hit create cluster, go to advanced options, and let's pick whatever, let's hit the next page. From a instance perspective, oops. Let me see where is the place you can change the so next page. Cluster, let me see, where is the image place? Not in this page. PC. Yeah, so here. Additional options. So what you're able to do is you're able to do a custom AMI ID by picking your own ID to launch your clusters. Here's another option as a EMR FS consistent view. This is also a very, very practical and important tips that what you do in the EMR cluster. Let's talk about this for 5 minutes because I think this is very, very important. So EMR consistent view, think about as, where's my, where is my, yeah. So EMR consistent view. So the EMR FS consistent view has to be drilled down to a fundamental design philosophy for S3. So S3, as you know, this is a storage, object storage. And so by default, the consistent it's eventual consistent. So what does this mean? I'm going to giving you some example on what does eventual consistent really means. Let's say, for example, as a user, you issue a write command. Let's say, you know, as a user, you say, okay, write abc.csv to S3. And the path is going to be S3, let's say, you know, WeCloudData, say data/abc.csv. And when you issue this write command to S3, so basically when this data going to S3, it doesn't really come back right away, you know, to be available from a, you know, availability perspective. So what I mean is, let's say you have another user. Let's say this is called user. Let's call this user 2. When the user 2 trying to, you know, reading this data, or, you know, at the same time, like when the actor, let's say, you know, when the user 1 saving, you know, reissuing the write command, and this command comes back, when the user trying to query this data right away. So it's going to be having a possibility to say, you know, is not ready. Despite the fact, actually this, let me make this a little bit cleaner. Otherwise this is going to, you know, adding some confusions. So let's just say we have only one user. This user issue a write command to S3. And from client perspective, this client come back saying, okay, I'm finished, which means, you know, the writing process returning back with say, okay, success, right? So now let's say, you know, this writing process finished. When this user trying to, you know, accessing this data right away after this write process comes back, let's writing this in a different color. Like this, a little bit larger. This is the write process. And when you finish this, you're going to, you know, let's say do another request, which is a read request. And when you're reading this, it's going to say, okay, this data is not ready, and come back with you as with exception. The reason for this is because object storage is following the design philosophy, which is called eventual consistency, which means the data will eventually replicate it to all the kind of endpoints. And when you know, it will take some time for this data to be truly ready. So it will be okay for some, you know, for majority of the use case, but for some of the kind of process who requires a strong consistency, which means whenever your write process come back as a success signal, it basically requires this data to be ready right away. So one way of, you know, doing kind of experiments, doing a precaution to making sure that data is available first before, you know, this writer comes back, is by implementing a thing called EMR consistent view, which means if you are actually clicking the features in here, saying EMR consistent view is equal to checked, then what you're doing in here is you are actually enable a services called DynamoDB under the hood. So this DynamoDB will basically do one thing. Since DynamoDB is a kind of like a massive key value pair services, the DynamoDB will storing this and then telling you whether this is exist or not. So this is one single kind of lookup table that basically pair with your S3 buckets. In that way, you won't miss a kind of like you won't meet a read by having exception saying, okay, it's supposed to be ready, but it's not ready because this you mentioned consistency feature for object storage. You can introduce an additional packages, which is doing simply by caching, what data already exist, and then when you're trying to reading the data, you can simply just come here and then checking whether this key value pair is available. Otherwise, you will gracefully returning back saying this particular key value pair is this particular object is not being created in S3 yet. So this is giving you a nice way to implementing a kind of a workaround with the features of inventory consistency with S3. So this feature has come out recently as well, which is very, very helpful and useful for your Spark transformation process in terms of during the staging phase. Yeah, so that's like a little bit extra things that I like to talk about. So AMI is something that you're able to bake yourself. And I remember we talked about a thing called Packer from HashiCorp. So Packer is basically a way that you can having a automatic way of generating and creating your own AMI images for different kind of use case, right? Think about Packer is kind of like a Ansible, or think about this is basically infrastructure as a code to generating a reproducible environment for different kind of a cloud vendor, right? So Packer able to basically you're able to write a shell scripts or Ansible kind of notebooks to generating a AMI image. So so the reason that people want to using their own AMI image is either because of for security reasons, they want to patch more kind of aggressive security patches on their EMR for let's say regular basis. If they see some thing need to be patched, and they will do those kind of exercise under the hood and just swap the existing MI by upgrading some of the packages, some of the binary files, and so on and so forth. So EMR, so basically there's a EMR 6.0 and also EMR 5 point whatever. The most recent version I think is 5.30 if I remember correctly. Yeah. So as you can see, by default, the 530 is being selected. So EMR 6.0 is also available for use. If you click on the 6.0, it has much less, beta, it has much less options. But for the 6.0.0, it's basically a little bit more advanced versions comparing with 5.30.0 in terms of the release version for software being tagged in here, and also some of the native AWS kind of services like actually comparing with 5.30 and 6.0, majority of the features are the same, but there's a minor change if we check AWS EMR release note. You can see what are the changes, 6 release version. So as you can see, the versions for the software has been upgraded for all those kind of major services. Let's see, your Docker runtime support. So you're basically able to can now run in the context of a Docker container, which is kind of new for EMR. So for this 5 point whatever release, you can't do you can't submitting a Docker image for Docker container for Yarn applications. Hive LAP support for query performance, and from JDK, Scala, Python. There's kind of like all kinds of major patches for 6.0, right? But as you can see, the default selection for the EMR versions to 5.30.0. The reason is because this is more reliable and more stable. But 6.0 is a little bit new. As you can see, it's already GA, it's already past the beta mode. But people prefer to using the 5.0, 5.30 release, which is the most recent release for 5.30, for the kind of stabilities out of it, right? So support versions of Hadoop, Who, Peak, Taz, Flink, and Zeppelin. I think it's really interesting here. Again, choosing EMR instance types. Okay, so use general purpose instance for master nodes. So master node has a computation requirements for file systems, job checkings, node coordinations, ecosystem application, and so on. So for a cluster with a small, think about, this is kind of like the main keeper for your whole cluster. So if you have a lot of instances in your cluster for task and kernels, then your cluster overhead is going to be bigger in terms of the back and forth traffic between your master node and with the core and task groups. It's going to be more communication overheads. And then in that case, to having a little bit bigger instance for your EMR core node is going to be making more sense and making sure that your cluster is going to be stable and reliable. Many jobs can also run on nodes that use general purpose instance. Use smaller instance types for testing, development, and smaller jobs. Use large instance type for production and larger jobs. I mean, the reason is because you wanna, if the job is super critical, you wanna making sure that you are allocating good amount of computation resource, including the CPU, including the memories, and also more optimizing kind of infrastructures like networks, like the disk IOs, so that you can really speed up your kind of a transformation process. So that's kind of like, how in generally you are, what's the rule of thumbs to picking the right instance for your, for your jobs, right? And by the way, the large or, to pick a larger instance or smaller instance is not kind of like a super kind of challenging tasks, but you have to keep one thing in mind, which is very critical. That we're going to talk about the how to optimizing your the Spark jobs. But think about if you have a physical machine like this. Let's copy 3 of those guys. Let's say if the worker has, for example, let's pick 16 GB, and let's say 2 cores, and it's applied, the same applied to the other work kernels. Now, if you think about it, so what you're able to do is you're able to, when you're trying to submitting a Spark submit. And then you have to give, for example, what's going to be the driver, memory, and then driver course. So driver memory by default, I think is either 512 megabytes, or it's 128. I don't remember which one. I think 512 is the default. The driver course is equal to 1, which is primarily coming from the EMR master node. For this two, I'm going to color code it so you know which configuration is coming from which one. And you will also do, of course, mode is going to be yarn. Sorry, master is yarn, and mode is equal to client. And this mode is equal to, it can be either client or cluster. And I'm going to talk about the difference between those two in a bit. But after that, you can say, exe. I'm going to changing the color for to the original color, and I'm going to say executor course equal to, say, for example, I don't know, 4, and executor memory equal to, let's say, for example, 14 GB, and there's some other parameter as well. But let's just say that first of all, the mode equal to, so master is yarn, and can be also Mesos, can be Kubernetes, can be standalone, can be yarn. So basically, you're telling your Spark driver to say submitting your job according to the yarn's kind of standard. So. And after that, the mode equal to client is basically, think about this is the way to telling your, your cluster, like where your driver application is going to be running at. So if the mode is equal to client, then the driver is basically going to running within the EMR master node, right? So this driver going to occupying this driver course equal to 1, and the driver memory equal to 512 megabytes is going to occupying the EMR master node, right? If you are changing this from client to cluster, then this driver will occupying the resource of the 512 and one core randomly in one of the worker nodes. So basically, this driver will be changing the kind of destinations based on the mode, right? Under the yarn master only. This is what we are discussing here, right? So the next configuration set I want to talk about is, let's say if you want executor course equal to 4 and executor memory is equal to 14 gigabytes. So now I want to ask you a question. Will this job being scheduled at all? Let's having also another important thing. It's called don't remember the keywords. I think non-executors. Non-executors, yes, this is the one. Number of executors equal to, let's make it 3. So if you take a look at this, do you think the yarn cluster will be scheduled this job at all under the condition that there's no auto scaling Let's say even though there's auto scaling is available, do you think this job will be scheduled? Oops. So the answer is no. The reason is simply because there's no, for the current instance types, there is no single kind of EC2 instance or the worker node well able to allocate enough of CPU cores for you. The 14 gigabytes may be okay. Depends on how many operational overhead each of the worker nodes going to occupy. Generally speaking, we talk about around like 10%-ish. So you have around 14 gigabytes of memories available. However, you're requiring 4 cores per executor, which this existing cluster not going to satisfy you. So at this point, the way you can do it is either by cutting this to, let's say 2, and then cutting this to 7, and then you're only you can actually having 16 here, and then you can this still as H3. This is going to work. This is under the extreme case that you executor is going to occupy a very small kind of resource footprints, right? But let's say if you are working with a big instance, like let's say the one that I'm having, like let's make it 194, and then let's say 36 cores, and of course you are able to allocating different kind of worker instance types within your cluster. That's called instant fleets, which is if you go to the next page, you're able to pick the instant fleets, which allow you to go up to 5 different kind of EC2 instance types. So you can say for example, this is like I have an M5 extra large for CPUs and 16 gigabytes. I can add another instance type, like let's say for example 2 extra large, and then let's say 24 extra large, and click save. As you can see, I have more options in here, right? But if you pick the uniform instance groups, you are only able to pick one EC2 instance types for task group. And keep in mind that this is a very important features. The reason is because if you are only depending on one single EC2 instance types, there is a possibility that AWS might running out of inventory on certain kind of regions. The reason the reason that usually running out very quickly is like US East 1 or US West 1, those some hot kind of data centers. We're running out of some popular inventory fast. So having a backup in terms of the instance types will allow you to scaling your cluster despite the fact that there is a possibilities that AWS will running out of inventory, but you have a more kind of a varieties in terms of the resource instance you're able to allocate to executing your job. So come back to this page. So now let's say if we have 36 cores and 194 gigabytes. And then, let's just make a little bit, let's say this is 24, 160, for example. And then let's say, we have 4 and 16. Now, let's say, for example, if you want to, schedule, say 4 cores and say, 26 gigabytes of memories. And then, let's see if we want to, allocating 3 executors. Then what's happening is your Spark cluster will basically do this. It's going to, okay, say I want a executor, which is like a container having 4 cores, and then 26 GB for memory. And in total, I want to, allocating 3 of this. So what this EMR master from your perspective, like your as the resource manager running here, will simply do, okay, let me examine it, what my resource pool looks like. So you have a resource pool that you have 3 workers available, and from a final granted perspective, you have like worker 1 with 194 GB and 36 cores. Does encode this. Worker 2, worker 3, 160, 24, 4, and 16. So in this case, that how many resources you have, but what you're asking for is like 4 cores and 26 gigabytes of memory. So you are going to see the available resource, and let's say if worker 1 able to, let's say if we take schedule the first job, second executor, and then third executor, and then if we are able to squeeze them in the the first worker nodes, then what it's able to do is it say, okay, worker 1, please schedule 3 GVM machines with this configuration, and I'm about to serializing jobs from a driver perspective to send it over to the worker 1, right? So at this point, you have 194 minus 26 times 3 and 36 minus 4 times 3. So this is what you end up with for the existing resource at the current moment, under the condition that you have only 1 job running. So yeah, so this is basically when we talk about picking the EMR instance types. Instant fleet is the best options for you to consider because you are able to having combinations like this, having different kind of instance types. And let's say, for example, if you are having a cluster like this, and then during the non-busy hours, right? You can scaling in to shutting down the big instance and only having the smaller instance like 16 gigabytes and 4 cores to be standby. Whenever there's a big job comes in, you can dynamically adding more instance like these big instance types and start growing your overall computation resource by adding more kind of heavy instance, right? In this way, you are saving more money on the idle times and gain more performance during the peak hours. Memory optimized for memory intensive jobs or in memory processing such as Spark, computation optimized, like it support. So basically, there's some jobs are more CPU heavies, like computation intensive, which requires a lot of kind of cores in order to make the job running a little bit faster. And there are some jobs that are actually more memory intensive, which means you're going to very aggressively caching some of the intermediate Spark kind of transformations kind of jobs and caching memory, and then and forking from that point and doing more transformations on top of that. So this is more like the memory optimized. Storage optimized is for heavy HDFS workloads, such as running a large HBase cluster. There's still, companies doing that, but you're going to see this kind of pattern is going to be rare and rare. People going to leveraging like, DynamoDBs, in AWS for, more kind of, performant and, saving more cost. GPU instance. So for some of the graphs like computations, which Spark has a computation called GraphX. What it does is try to, let's say, if you have a traverse throughout the kind of node within the graphs kind of database, or graphs kind of kind of scopes or diagrams, then using GPU will helping you to boost the performance quite a bit. So you are able to allocate a GPU instance within your Spark cluster, and there are certain types of work that has been optimizing for Spark, to gaining more performance and making the job running much faster. GPU. Let's see what GPU jobs are supported for Spark. It's not a good one. Yeah, so using NVIDIA GPU drivers, CUDA, which is one of the computation frameworks from NVIDIA, CUDN. So a majority of those kind of GPU at this point is more for a machine learning process. For some standard transformations, generally speaking, you don't gain a lot of performance boost for the standard for the GPU. The CPU is probably running much faster, but for some of the machine learning process, actually much faster with kind of GPUs enabled instance. So red instance, yeah. Consider following on choosing instance: core count, memory size, storage size, and types. Network is also very important, especially when the nature of your job involves a lot of shuffling. The network capacity is very important, right? If you have a huge amount of shuffling happening within your cluster. And also the CPU technologies, like which vendors that you are using for each of the instance is also very important. I think AWS have their own CPU. I think AWS developed their own CPUs, or I don't remember exactly what's the name. Intel Turbo. Yeah, Graviton, yes. So AWS start to develop their own CPU processor, which is called Graviton. I think this was released during the last kind of reinvents. So this Graviton processor is actually, think about this is a competitor with the Intel. It's actually running in their existing EC2 instance for some of the instance types. So just be careful. But majority of the time, you're still dealing with Intels. But gradually, I think AWS is going to replace majority of their CPUs to their own kind of a processor. This is called Graviton. Resizing an EMR cluster. I think we briefly talk about this. add remove core task nails using console CRI or API. So you're able to dynamically kind of adding or reducing the total number of instance for core and task nails. But you can't do anything with the master node once it's already setting up properly, right? Adding core node to increase the processing power and HDFS storage. So, so basically think about this way. If your job is requiring HDFS, then you have no other option but increasing the total number of instances in core nodes. So if you purely intention is to adding more computation resource and treating those resource as referral, which means this is going to be a short-lived computation resource, then it's always wise and reasonable to scaling in and out for the task nodes. So let's take a quick look. So let's say if you have your EMR cluster right now, let's say this is the master group, of course, and let's say this is a core group, and this is, for example, task group, and let's make it this different color. Let's say if you are trying to scaling the total computation resource by introducing more CPU and memories to your existing cluster, always adding more things like this will making it very, very easy to scaling in as well as scaling out. Comparing with purely scaling, the kind of core groups. The reason is because this. I mean, this is so this is very kind of like important kind of tricks to follow. So if you think about from if you are, let's say, the developer who being assigned to working on these scaling features for AWS EMR, what are you going to do, right? So if you are trying to scale out, let's say, the core group. So what process you need to follow, right? So step one is to, say, judge or to observe how many instances we have right now. And the second is, what is the target instance count, right? And the third one is, okay, let's introduce an instance under the core group. Install Yarn kind of application related kind of software or package to install, and then install HDFS and install other necessary packages, and then join Yarn, join existing node to Yarn cluster, and what's next? Let's see. So after you're joining the the existing node to Yarn cluster, you have to join the existing HDFS data node to the existing cluster. And then, but this requires a lot of work from the existing cluster. The reason for that is, think about, if you want to introducing another one, And let's say if you're already having data who's, which is available within this cluster, now if you're introducing one more node, the data has to be shuffled a little bit from the existing worker node to the new worker node in order to be properly balanced and properly partitioned within your cluster, right? So think about how much time this process is going to take in order for your core groups to be available before everything comes back properly, right? But if you talk about just this task groups, majority of the steps are the same. However, there's no HDFS. No HDFS, no joining, no waiting whatsoever. So just the rest of the installations and boosting process, this will be much faster, right? And this process seems apply to the other way around, which is actually more painful. If you're trying to, let's say, gracefully downsizing the existing core groups, what you have to do is you have to, for the existing data under this core group, you have to properly replicate it back to the rest of the remaining worker groups so that you don't get any data lost within your cluster, right? And only under that case, this existing worker core groups can be decommissioned, and then and making sure all the data is actually available within these worker core groups. So that's kind of like taking a lot of extra cycles for your cluster to scale in. Comparing with task groups, because it's inferral and stateless, which means it doesn't carry any stateful information on the worker nodes, on the task group. So under this case, what you're able to do is you can simply just shut it down, and the rest of the worker node, the task group's workers nodes will be doing just fine, because there's nothing that these guys will be caring about the things in here. But from a Yarn resource manager perspective, Yarn have to making sure that once it's lost the heartbeats with the worker task node, it need to start to shrinking the existing resource pool by cutting down the corresponding decommissioned worker node resource out of this existing resource pool, right? So I hope I explained this properly. Like when you're trying to just simply adding more computation resource by CPU and memory, this is way to go, right? The scaling in and out and applying the scaling policies on only the task group is making perfect sense and is going to working perfectly. But if your scaling policy will involve a core groups, then you have to think about how to do that properly accordingly, right? So those kind of the two considerations I want to sort it out, and hope you can pay attention to. Shrink cluster by removing nodes. So core instance groups can be resized if needed. Resize the task group to regular capacity between steps. Resizing an Amazon EMR cluster. Dynamically resizing allows you to adding nodes to twin cluster to optimizing your application. On-premises cluster administrator must twin their applications to optimizing the cluster usage. So dynamic resizing is based on your custom logics, which we show during the beginning of the class. So you are able to do a enable cluster scaling and click on 530. enable cluster scaling, and you can pick either the EMR manage scaling, and you can also pick the create a custom automatic scaling policy, right? And you can changing the scaling policies kind of, that best serve your scenario. And we talk about, there's a lot of, kind of if conditions you can pick by memory, by, CPU, by network, by, total capacity of the your nodes, your containers, and stuff like that. So this kind of training process is automatically comparing with on-premises. You have to basically, think about collecting all the metrics and then, scaling in and out your cluster accordingly. But all those kind of process requires a lot of kind of special skills, as well as, maintenance window in order for this to be kicked in. Sending work to an Amazon cluster. So we talk about, there's the steps you can follow. And for our final project, we're going to using steps, which is kind of units of works, can be sent to cluster in several ways, provide entire work definition in map and reduce functions, typically for trending cluster. So steps can be also used for a long running cluster, but for some of the configurations like, what's going to be the termination behavior? It's not going to be defined on the step level, but it's more on the cluster level. Creating a long-running cluster and using Amazon EMR API to submit steps containing one or more Hadoop jobs. Creating cluster with ecosystems applications installed, Pig, Impala, and Hive, using application interface to submitting queries by scripted or interactively. So if you install, let's say, Hive and Pig and Impala and using application, so this, let's say Hive, you can query the data in Hive through Beeline, through the terminal. But let's say, for example, if you're trying to, using Presto or using, let's say Pig or using Hui, it's come and also using, let's say, Livy, it actually come with a interface, which should come in with a UI, which you can basically go into the default port on the EMR services and start interacting with your cluster. So one thing I'd like to show you is, let's say, EMR services default port. So as you can see, this is a way of querying the data, which is kind of like a UI interface running on port 8888. Jupyter Hub is running on 9443. Think about Jupyter Hub is kind of like Zeppelin, but it's more Python kind of friendly. And Livy is running on 8998. Yarn running on 8042. Ganglia is running on port 80 and slash Ganglia, right? So you can check the default application ports within this page and look and getting the information accordingly. Create long-running cluster, connect and submit Hadoop jobs using Hadoop API. This is also another way of doing it, but we talk about SSH into the node and and then do Spark submit through the terminal. By default, steps run sequentially on the master node using FIFO, first in first out scheduler. Configure file scheduler, a file scheduler for concurrent jobs. Steps can be added while cluster is running. You can register the steps through console API or CLI. So in our final project, we're going to register new steps with EMR cluster, and it's going to through API, through Boulder3 command, Boulder3 library. And Bootstrap actions can only be supplied when cluster is launched. So when we launch the cluster in the first beginning, there is a launch scripts that you're able to define. by saying what you are. Let's see where the log script. Terminated. Advanced options. Can define a step. Next. Yeah, so here is a bootstrap action. So what you're able to do is you can say custom actions, and you can define a S3 script, which is a bash scripts in here, which means these scripts will, let's say, if your script is like, a shell scripts. Let's say what you do is, like, say, do some like, yum install, do, pip install, and copy from location 1 to location 2. Those kind of a warm-up bootstraps is only available during the initial launch phase. Once you pass that phase, you can't do this anymore, right? And the bootstrap actions will apply to the newly added kind of instance to the different kind of groups as well. Steps can be resolved in multiple Hadoop jobs, interactive Hive programs. Using Amazon S3 as your, okay, so let's talk about what is the best practice for Amazon EMR clusters, right? So using Amazon S3 as your persistent system of records. This is kind of rule of thumb, and that's why you can see that this is putting on the top of the list. Using S3 as a persistent layer will making your life much easier, and less worried about scaling in and out for the core groups. Using transit cluster as much as possible, and this is kind of I think I briefly talk about there is a new patterns called kind of a trigger once architecture, which you think about you're only going to spin up your computation resource whenever there is a job comes in, and then once this job finish, what you're going to do is you're going to shut it down and and reclaim the resource back. In this way, you're making your your kind of operational budgets into a very, very low level, and also you have less operational concerns in terms of upgrading or patching your AMA image. You can doing this at any time you want, and just doing a structure or a parameter change within your submission kind of steps, and you're able to do those kind of upgrades on the fly, which is kind of like a very, very neat feature, right? Resize cluster and use the EC2 spot instance to more efficiently manage capacity, performance, and cost. So this is quite kind of important tips for you to consider using spot instance to saving the cost. Sometimes the spot instance can be like 50 to 70% cheaper than the on-demand price, right? So if you are using fleet instance and combining a bunch of spot instance options, this is going to save you cost significantly, and reducing the kind of overall operational kind of overhead from the by introducing spot instance. So we talk about how we are able to introducing spot instance into our kind of a setup. So the default is uniform instance groups. If you just click on instance splits, so think about, you don't need to worry about running. Let's say if the ask is you have to save costs and have to introduce in spot instance. So if you're using uniform instance groups, you have no other option but whenever there is you know, a case that, you know, the AWS is running out of, you know, like the EC2 instance for the, you know, types you need. You have no other options but, you know, to wait and terminate your existing cluster, and you know, and waiting the resource to come back, right? Which is probably not something you're looking for. So another way you can do it is by introducing instance fleets, by, you know, configuring up to 5 different kind of instance groups, and you can changing the, you know, on-demand units, and you can, you know, define the durations of, you know, how long this is going to, you know, to run until the different duration period ends. And you can say how many combinations, like how many is on demand and how many is on the spot instance, right? So which is kind of convenient for you to define different kind of combinations. So, you know, if you're not lucky, if you're running out of, you know, a couple of spot instance inventory, you still have other, you know, instance types available, you know, for you to bid on the spot instance, right? So giving you much confidence that your, you know, resource will be there, you know, and you're going to save a lot of, you know, cost on this, you know, spot instance, instance fleets options. Move to new instance families to take advantage of the performance monitoring to determine when to resizing or change instance types. Share a persistent Hive metadata store in RDS among multiple EMR clusters. So, you know, people, so we can using Glue for this right now. This is, you can using RDS to holding your Hive metadata store, or you can using Glue, which is, you know, kind of very neat features. So you can, you know, caching all those information in Glue as well. Using AWS Glue data catalog tools to automate data discovery and organizing data assets. Amazon EMR outputs. So can be saved output to Amazon S3. Hadoop jobs, log files, and debug files can be saved into S3 as well. So those debug jobs and debug and the logging files are very important for you to, you know, troubleshoot and keep track of, you know, your performance and various other kind of metrics, you know, for your computation job. Result format you can using, you know, default MapReduce. You can using output format interface. Hive using serializer, deserializer to change the formats. S3 to allow data to be shared with other cluster and AWS services. Okay. So what is the difference between a transient and long-running cluster, right? So this is a very important concept. We talk about it over and over again. And I hope you, you know, as a data engineer, this is very kind of interesting and very important topics to discuss and to understand with your peers and with your managers, right? Because this involves cost, operation models, as well as, you know, performance tuning and stuff like that, right? The master node instance count is set to 1 by default and cannot be changed. So we talk about it like by default is setting to 1. And so currently we're able to do a multi-instance of master. We can say, where's the option? Yeah, so here, use multiple master nodes to improve cluster availability. So you are able to define a multiple kind of master node in the first page by making sure that your cluster will always be always up and running. This feature is essentially, you know, very, very helpful and useful for the long-running cluster. But for referral, the odd or the chance that the cluster will running into issues will be really, really low. So, you know, this is not going to be, you if you're running, so generally rule of thumb, if you are running a job in a transit cluster, you don't need to select the multi-master nodes. However, if you're running jobs in a in a low-running cluster, having this to be selected is is basically going to increase your overall availability as a cluster. Jobs that run sequentially by default is equal to true, which is FIFO, first in, first out. And then you can change to a fire scheduler, if this